Today's lesson is related rates. This is one of my favorite. Anyway, you're talking about the rate things are changing depending on something else. All right. Like how fast is the circumference of a circle changing with respect to its radius? All right, so we start out by having all these formulas because every time you read this problem, you have to decide which equation do I need to solve it. Because you're going to take the equation, then you're going to do implicit differentiation with respect to time. Instead of, we just did implicit when we did dy dx, and we differentiated y in terms of x. Today we're differentiating with respect to time, so we're going to have a dx dt, we have dv dt, okay? We have dy dt, dr dt. Everything is with respect to time because it's at a different time period. The rates are going to be different. All right, so you have a circle, and it's growing. It starts here, and it gets to here. It gets to here. The areas is changing. It depends on what point in time we're looking at it. So anyway, getting ahead of ourselves. Here's the formulas. Pause it for a minute. Write them all down in your notes. On the AP exam and our tests, we always give you the formula because we're not testing whether you can memorize formulas. We're testing whether you know how to do related rates. So the formulas will be given on the problems. Okay? Then, so I assume you paused, you wrote them down. It's time to get going. All right? The idea here is to sketch the problem, write the words along with what you're finding out. In other words, write down what's given, write the equation you need, and this is, what are you trying to find? Okay? Differentiate with respect to time, substitute the values in after you differentiate, and solve. Don't forget to label with units. Okay? AP exam always has a related rates problem. You forget the units, you lost 1 out of 9 points. All right? That's silly. Don't do it. All right, so the first things we're going to do is practice differentiating with respect to time. So they gave me the equation in this case, so I didn't have to know what it was. So first differentiate with respect to time. So we have dy dt equals 2x dx dt. Derivative of 3 is a constant is 0. Now plug in what you know. They told us dx dt is 2, and they told me x is 1. So dy dt is equal to 2 times 1 times 2, which is 4. And it didn't give us any units, so we're good. Okay? Let's see. Let's do this one. You have dy dt is equal to 2x dx dt plus 3 dx dt. Plug in what you know. They told us dx dt is equal to 2. X is 3, so dy dt is equal to 2 times 3 times 2 plus 3 times 2. Oh, it's a minus sign. I knew something was wrong. I think that's not the answer I got the first time I did it. This is a minus. That should be a minus. So what do you have? 12 minus 6 is 6 times 2 is 12. Done. Now let's do ones that you're going to see on your test. I don't ask you these. Those are just practice. All right? All right. On this worksheet, let's do this one first. I'm getting ahead of myself. So they're looking for dv dt. Pi over 2 is a constant. This you have to do the product rule. So first times the derivative of the second plus the second times the derivative of the first. All right, they're complicated. Don't forget the product rule. All right, so these problems, this one was talking about area of a circle, and there were 2 of them. I worked one. I'm going to do one with you so you can watch. Here, they're talking about volume, same problem, different numbers. Okay, so I'm going to work one, look at the second one, see if you understand what I did, and that's how we're going to do the rest of this worksheet because there's lots of problems on it, okay? All right, a pebble is dropped into a calm pond causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a rate of 1 feet per second. When the radius is 4, find the rate at which the area disturbed by the water is changing. All right, the thing is you don't want to plug in these values until after you differentiate. So I'm going to do dA dt equals pi 2r dr dt. Now you plug in the values. What are we looking for? Find the rate, the area. So we're looking for dA dt. So you plug in the pi's there, the 2's there, the radius at 4, and the rate of change is 1. So I end up with 8 pi square feet per second. It's area, you have squared feet. Okay? Same type of problem. Okay, the area is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic meters per second, or centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50? Make sure you pay attention to diameter. So r is equal to 25. Okay, take the derivative with respect to time first. dv dt equals 4 pi over 3 3r squared dr dt. The volume's increasing at 100, so 100 goes here. These 3's cross out, so you end up with 4 pi. R is 25 squared dr dt. So now you just need to solve for dr dt. So you get 100 divided by 4 pi is 625. So let's see, what is that? That turns into 25. So that equals 1 over 25 pi. And what? What are we talking about? The radius is changing, so it's going to be centimeters per second. Okay, you take the derivative with respect to time first, then plug in your values, then simplify. And you notice I left it in terms of pi. Don't give me a decimal out of your calculator. Just don't. All right. The radius of a right circular cylinder is increasing at a rate of 4 centimeters per second, but its total surface area remains a constant 600 pi centimeters squared. At what rate is the height changing when the radius is 10? I got the wrong formula here, though. We want surface area. Okay, so what's my surface area formula? Surface area of a sphere. Oh, it's a cylinder, isn't it? So the surface area of a cylinder is the radius times the height. Radius times the height plus the area of the top, which is 2 pi r squared. All right, because you have the top and bottom. Oh, this is a good problem. Surface area. The radius is increasing and its total surface area remains constant. All right. So if that's 600 and the rate when the height is changing, the radius is 10, we don't know the height, right? So we can solve for that. Well, let's do this first. So I take the derivative with respect to time. If this is constant, this is the derivative 0. This is a product rule, so you have the first times the derivative of the second plus the second times the derivative of the first plus 2 pi times the derivative of that, which is 2r dr dt. All right, 0, r is 10, dh dt is what I'm looking for, plus h, I don't know h, so we'll come back and get that in a second. Dr dt is 4, plus 4 pi times the radius is 10, times dr dt, which is 4. So all I need is h. Well, side thought, they told us this is 600. So 600 is the surface area when r is 10, h plus 2 pi, r squared is 100. Okay? So you have 600 minus 200 pi over 10, which is what? 60 minus 20 pi. Ooh. All right, so let's plug that in. So I've got 0 equals 10 dh dt plus 60 minus 20 pi times 4 plus 160 pi. Okay. So let's clean it up a little bit. 10 dh dt plus 240 minus 80 pi plus 160 pi. So I move this over here and you get negative 240. Yep. 80 pi minus 80 pi equals 10 dh dt. You divide by 10 and you get negative 24 minus 8 pi equals dh dt. What are my units? Centimeters per second. Okay, so if the radius is increasing and the surface area is staying the same, the height has to be reducing, and it's negative, so that makes sense. So dh dt equals negative 24 minus 8 pi centimeters per second. Wow, that was tough. Okay, this one was a cone, and I worked it out. I changed my mind. We're going to have to do this one for you. So let's take this out of here, and we'll do it again. Okay, aluminum cans full of liquid has sprung a leak of 10 cubic inches per minute. This can has a height of 10 inches and a radius of 4. What is the rate at which the height of the liquid is falling? Okay, this is the product rule. Find the derivative first. dh dt pi first times the derivative of the second plus the second times the derivative of the first. Okay, this is dv dt. The pi. R is 4. 4 squared is 16 dh dt. Plus the height of 10 times 2 times r is 4. dr dt. Do we know that? Is the radius going to change as the liquid seeps out? Here's your can. Okay. There's a hole in the bottom. It's all leaking out. The height is going down. Is the radius changing? No. So it's 0. Ooh, good problem. Thought we were stuck, huh? 16 pi dh dt. So dh dt is equal to 10 over 16 pi, which is 5 over 8 pi inches per minute. Get used to answers like that, all right? This is another right cylinder. I did the same problem, and it was decreasing. Ooh, should this be decreasing? It probably should be negative. Why isn't it? Oh, because this should be negative. There you go. There it is. Alrighty, here's the cone. These are good. There's always a cone problem. I love the cone problems. Okay, water's pouring into an inverted cone. Think of a coffee filter, okay? And the height is 16 and the base is 4. So this is 4. This is 16. Okay. 2 cubic meters per second. So that's volume. That's dV dt. How fast is the water level rising when it's 5 feet deep? All right. The thing is you're putting water in here. You're ending up with a bunch of triangles that are similar. So the ratio of R over height is going to stay the same as it originally was. So R over H is 1 over 4. That's an R for radius. Okay? And that's important because what are we looking? How fast is the water level rising? So we're looking for dH dt. We don't know dr dt, okay? But if I can rewrite this problem so there's no r in it, then it becomes an easier problem. So you're going to use this ratio that 4r is equal to h, but really I want r is equal to h over 4. Okay? And I'm going to replace r with what it's equal to before I find the derivative. So r squared, so that's h over 4 squared. So now I have v equals pi over 3 h squared times h is h cubed over 16. So that's pi over 48 h cubed. It's an easier problem now. Now you do dv dt. You get pi over 48, 3h squared dh dt. And now you plug in the data they gave us. They told us dv dt is 2. H is 16. No, it's not. They want to know what happens when it's 5. See, 3 goes in here, so that's 16. 16 times 2 is 32. Divided by 25 pi equals dH dt. I don't think I can clean that up. So 32 over 25 pi. The height is changing in what? Meters? Per, what's our unit? Minute. Okay, the key to these problems is this ratio over here. The ratio they tell you right at the beginning of the problem. And you make a substitution depending on if you're looking for the rate of change of the height or the rate of change of the radius. Okay? Or the volume. All right, so here's another cone. We're looking for dH dt. We rewrote it in terms of h. You use the same ratio, and I did the same problem. Follow along, see if you can see where it went. Okay? All right, ladders leaning against the building. Okay? So here's my thing, the x, y, here. This is the ladder. Okay, and the ladder slides away from the building, so it's going this way at 2 feet per second, so that's dx dt is 2 feet per second. And they want to know how fast is the ladder sliding down the building, so they want to know dy dx. Okay, so they told us the ladder's 20 feet long. So in this story, that ladder, that is not changing. There is no dl dt. Because the length of the ladder doesn't change. It's a constant. So my equation is a squared plus b squared equals c squared. X squared plus y squared equals 20 squared. Now I take the derivative and you get 2x dx dt plus 2y dy dt equals 0. I'm going to divide by 2 just because it makes my number smaller. So I got x dx dt plus y dy dt equals 0 divided by 2 is still 0. Now plug in what you know. Well, they told you 20 feet above, how fast when it's 12 feet above the ground. So we know y is 12. So this is 12. We're looking for dy dt. We know dx dt is 2. Well, what's x? Well, this is a right triangle, right? If this is 20 and this is 12, it looks like it's a 3, 4, 5, right? Because this is 5 times 4. This is 3 times 4. So 4 times 4 is 16. So this is 16. And they usually do that. They're pretty triples. They're not making you get out your calculator to figure that out. Okay? So know your triples. And that equals 0. So let's see, that's 32. So you have dy dt equals, subtract it, negative 32 divided by 12. You can divide both by 4, right? Negative 8/3 feet per second. And it's negative because it's sliding down. Okay, y is getting smaller. There's another example of the ladder. Okay, oh, the ones with angles in them, I love it. Okay, the balloon is rising, so I got a balloon over here. It's going up in the air at 3 meters per second. You're standing over here 30 meters away watching it. Find the rate of change of the angle of elevation of the balloon when the balloon's 30 meters above the ground. So my picture's not right. It's a 45-degree triangle, okay? But I need an equation to represent this. Opposite over adjacent is tangent. So I said the tangent of theta is equal to y over x. Because that's in the y direction. That's the x direction. Okay? And then I did x times the tangent of theta equals y, just so I don't have to use the quotient rule. And x is a constant. You're 30 meters away. It's always going to be 30, so you can replace that with 30. Oh, and now you take the derivative, okay? So you get 30 times the secant squared of theta d theta dt equals dy dt. And now you plug in what you know. It's rising at a rate of 3, so that's this. D theta dt is what we're looking for. We need to know the secant of my angle, okay? Well, secant is a reciprocal of the cosine. The cosine is adjacent over hypotenuse. This is a 45-degree triangle, so it's 1 root 2. So this is 30 root 2. So my secant is 30 root 2 over 30. Well, these guys cross out. Square root of 2 squared is 2. So you end up with 60 d theta dt equals 3. So d theta dt is equal to 3 over 60, which is 1 over 20 radians per second. I love those problems. All right. There's another angle. Work. Oh, whoa, come back. Work those. Okay. This one is a tough one. All right. A boy 5 feet tall walks at a rate of 4 feet per second directly away from the street light, which is 20 feet above the street. At what rate is the tip of his shadow changing, and at what rate is the length of his shadow changing? Ooh. Okay, so here we are. This is 20 feet. The boy's walking away. He's going this way. He's 5 feet tall. Okay? And he's walking this way at a rate of 4 feet per second. Okay? So what happens is you have a triangle. And they're asking you for how fast is this changing. And what rate is the length of his shadow changing? And we think that's 4 feet per second. We know this rate is changing at 4 feet per second. We don't know that rate is feet per second. Okay? Just think about it when time goes by. He's over here, that your 5 feet's here, right? I have to think about that one. I know how to do this one. It's getting closer. The rate is coming in. You have a ratio. But we knew that distance. I don't know. We're going to have to come back. I'm going to have to look at that one. You're going to do this one, though. I set this one up as a floodlight on the ground. So here's the light shining on the guy that's 2 feet tall. And I said, this should be S. Sorry, let me change that. I changed it halfway through it. His shadow is projected there over the length of this whole side. All right, that gives you a ratio. And then I said, well, wait, this is changing, right? This is constant, but this distance changes by 15. And I cross multiplied, and then I took the derivatives, and I plugged in what I knew, because this was 6 meters. So this is -6, because R is getting the distance to the thing keeps getting smaller and smaller and smaller. I ended up with 1/5. We're going to have to come back and look at that one. Might have to put an addendum on and send it to you. Okay? That's a tough problem. I've never seen one. I left this one on purpose because this is a tough one. It says the height of a cylinder is 12 centimeters and the radius is 4. Okay? There's circumference of the cylinder is increasing at a rate of the circumference of the cylinder is increasing at a rate of pi over 4 centimeters per minute. And the height of the cylinder is increasing 4 times faster than the radius. Okay, how fast is the volume of the cylinder changing? So we have the volume of the cylinder. It talks about the circumference of the cylinder. The circumference, right, is 2 pi r. If I take the derivative of that with respect to time, you get 2 pi dr dt. Okay, they told us that the circumference of the cylinder is increasing at a rate of pi over 4. So I can solve for dr dt. So you divide by that, and you get 1 over 8. So it's pi over 4 times 2 times pi. Yeah, equals dr dt. These guys cross out, so you get 1 over 8 centimeters per minute equals dr dt. And then you go and do this. It says the height of the cylinder is increasing 4 times faster, so you multiply it by 4, so it's a half, is dh dt. Now you have to do the derivative of that. So v is equal to pi, product rule, r squared dh dt, plus h times 2r dr dt. Okay, so you get pi. R squared, r is 4, so that's 16 times dh dt, which is a half, plus h, which is 12, times 2, times 4, times an eighth. We just have to clean it up. Oh, so that's 8. These guys cross out, plus 12. That gives me 20 pi. Is an option? Yep. Cubic centimeters per minute. Good problem. You had to do this one twice because that gave you the rate of change of circumference. That led you to dr dt. The wording gave you dh dt. Then don't forget the product rule. Good problem. Okay? And I will come back Maybe I'll do this one in class tomorrow. So come to the Zoom and watch.